Alright, let's compute the expected value of a negative binomial random variable. The negative binomial distribution model situations, such as a sequence of coin flips, we're interested in knowing, say, when you get the third head. The probability mass function for this distribution is n minus 1, choose r minus 1, times 1 minus p to the n minus r, times p to the r. And r is the success number that you're interested in, and p is the probability of success on each trial. So in my coin flip example, r would have been 3 because we were interested in when we got the third head, and p would have been 50%, assuming we had a fair coin. The possible values that n can take on are r plus 1, r plus 2, etc., and this is called the support of the random variable. Okay, to get the expected value of y, we have to compute this insane summation. Before we do that though, let's give ourselves some simplifying results that'll make things way easier. So the first result is something that transforms binomial coefficients into derivatives. So an example is as follows. If m is 3 and k is 6. I'm going to do the example in the opposite order. I'm going to start with the right hand side here, and I'm going to get to the left hand side. It's easier to do it this way. So if m is 3 and k is 6, then I get 1 over 3 factorial times the third derivative of x to the 9th. The third derivative of x to the 9th is very easy to do. You just bring down a 9, an 8, and a 7, and reduce the power to a 6. And then 9 times 8 times 7 is 9 factorial divided by 6 factorial. So I get that down here. And then 9 factorial over 6 factorial times 3 factorial is a binomial coefficient. It's 9, choose 3. And then if we go back to our m and k, we get what we were hoping to get. The next result transforms a single summation into a difference of 2 summations. The reason this is helpful is because this one right here is geometric, and this one is an m minus first degree polynomial. You'll see why this is useful in a few minutes. An example of this is let m equal 3, you plug in 3 for m, you get this summation. If k starts at 0, then we start with x to the third, then we get x to the fourth, then we get x to the fifth, etc. Now I'm going to add 1 plus x squared to the front and subtract it from the back. Now this whole thing at the front is just a geometric series, which is right here. And then at the back we just get the series 1 plus, or not even a series, but the sum, 1 plus x squared. And that's this right here. And if we go back to m, we get m minus 1 here. The next result is just what a geometric series is equal to. I'm not going to do an example here just because people already most likely know this. Just keep in mind that in order for this to be true, the absolute value of x has to be less than 1. The final simplifying result is just the mth derivative of 1 over 1 minus x. That's equal to m factorial over 1 minus x to the m plus 1. And here's an example here. You can pause the video if you want and look through this, but I'm just going to say that I'm going to point out one thing, which is that the fact that you have a minus in the parentheses, that is going to prevent you from getting negative powers. So every time you compute a derivative, you're going to bring a negative power in front of your 1 minus x to whatever, but the negative is going to get canceled by the fact that you have to use the chain rule. You're going to have to multiply by -1 every time you take a derivative. So that's why you don't have something like -1 to the m plus whatever power here. It's just a clean m factorial over 1 minus x to the m plus 1. Okay, let's calculate. So here's the summation we started the video with. It starts with an index of n equals r, which we don't like, so we're going to change that by making a substitution. We're going to say let k equal n minus r. And if we do that, then n is going to be equal to k plus r. So what we're going to do is we're going to replace all the n's with k plus r's. This one, and this one. And that's going to also make our index start at 0, which we like a lot more. Now we have r minus r here, that's going to be 0. So we're just going to have 1 minus p to the k. And I'm going to pull this p to the r outside the summation here. Okay, now what I'm going to do is I'm going to make another substitution. I'm going to say let x equal 1 minus p and m equal r minus 1. Since p is a probability, 1 minus p will be less than 1 in absolute value. That's going to be important when we use the geometric series up here. So that's going to make the summation look way nicer. We're going to get that. And then what I'm going to do is I'm going to split the summation into two pieces over this k plus r. So one of them is going to have a k, the other one's going to have an r. Okay, so what I'm going to do now is sort of a trick. I have x to the k here, but if I pull one x outside the summation, I now have k times x to the k minus 1. Well, what does that look like? That looks like I took the first derivative of x to the k, which I did. So I'm going to replace k x to the k minus 1 with the derivative with respect to x of x to the k. And I'm just going to pull the r outside of this summation here. That's all I did on this side. The summation is in terms of k, so the r can be pulled out. All right, now what I'm going to do is, since the differential operator is linear, I'm going to pull it outside the summation. And now I'm going to say let s equal this summation here. Notice that that summation appears right here on the right and here on the left. So I have that same summation appearing twice. So I get p to the r times x times the derivative with respect to x of s of x plus r times s of x. And this will be our intermediate conclusion. Expected of y is equal to this right here. Okay, now we need to compute s of x. So we'll store our intermediate conclusion up here. All right, s of x was defined as being this summation here. So we're going to apply our first simplifying result, which turns this binomial coefficient into an mth derivative. And what we can do is, since the differential operator is linear, we can pull it outside the summation. Okay, now we can apply our second result, because we have this right here, which is exactly this. So we turn that single summation into a difference of a geometric series, and then this other summation here. Now the nice thing is, this is an m minus first degree polynomial. If you take the mth derivative of an m minus first degree polynomial, it must be 0. So that's going to go away. We're just left with this stuff times the geometric series. Now we can use our third result, which is the geometric series is just equal to 1 over 1 minus x. And we already said earlier that since x is 1 minus p and p is a probability, this condition is satisfied. Now we can use our fourth result, which says that the mth derivative of 1 over 1 minus x is m factorial over 1 minus x to the m plus 1. And then those m factorials can cancel. So that's what s of x is equal to. This will be our second intermediate conclusion. Start that up there. Now let's finish our computation. We can plug what we know s of x is equal to in for these two locations. It's going to look a little bit nasty for a second, but just plug that stuff in. We get this. And now we take the first derivative of this thing. Well, that's just going to bring the m plus 1 down as a negative power, but then we're going to multiply by negative 1 from the chain rule. So we're going to get a positive m plus 1. And then nothing's going to happen to this one yet. Okay, now we can go back to our substitution up here. X is 1 minus p and m is r minus 1. So that's going to simplify things quite a bit. The x is going to be 1 minus p. M plus 1, well, that's just going to be r. And then r stays, and then this m plus 2 is going to be r plus 1, and then this m plus 1 is just going to be r. And I'm going to distribute the p to the r into everything. So if I simplify these a little bit, I'm going to get this. And I left one of the p's here just so I'd have a common denominator. But now I can distribute this r in here, and I can add the two fractions together. And now p negative pr plus pr, that's just 0. So I get my result, which is r over p. And the conclusion that we were looking for is that expected of y, which is this insane summation, just simplifies to r over p. Thank you very much. I'll see you next time.